Problem number 2 from the International Mathematical Olympiad, 1959. For what real values of x does the expression square root of x plus square root of 2x minus 1 plus square root of x minus square root of 2x minus 1 equal a? We need to find x for three values of a, root 2, 1, and 2. Only non-negative real numbers are admitted under square roots. Before we start solving, let's figure out where this expression is even defined. For the inner square root to make sense, we need 2x minus 1 to be at least 0, which forces x to be greater than or equal to 1/2. And since we're summing square roots, a must also be non-negative. These two constraints hold throughout the entire solution. Now let's square both sides. Expanding the left side, we get x plus root of 2x minus 1, plus twice the product of the two square roots, plus x minus root of 2x minus 1. The first and last terms are clean. The square root of 2x minus 1 cancels, and they simply add up to 2x. So we're left with a squared equals 2x plus twice the square root of the product of the two expressions. To simplify that product, we use the difference of squares identity. A plus b times a minus b equals a squared minus b squared, with a equal to x and b equal to the square root of 2x minus 1. The product becomes x squared minus the quantity 2x minus 1, which simplifies to x squared minus 2x plus 1. So now we have a squared equals 2x plus 2 times the square root of x squared minus 2x plus 1. Here's the key observation. The expression x squared minus 2x plus 1 is a perfect square. It equals x minus 1 all squared, and the square root of a perfect square is the absolute value. So we arrive at the clean and elegant formula. A squared equals 2 times the quantity x plus the absolute value of x minus 1. This is the central result that drives everything else. Now we split into two cases based on the sign of x minus 1. Case 1, when x is less than or equal to 1. The absolute value of x minus 1 equals 1 minus x. Substituting in a squared equals 2 times x plus 1 minus x, which equals 2 times 1, which is simply 2. So a equals the square root of 2. And crucially, this is constant. It doesn't depend on x at all. This means the equation holds for every x in the interval from 1/2 to 1. Case 2, when x is greater than 1. The absolute value of x minus 1 equals x minus 1. Substituting in a squared equals 2 times x plus x minus 1, which gives 4x minus 2. Solving for x, we get x equals a squared plus 2, all divided by 4. For this solution to actually satisfy x greater than 1, we need a squared plus 2 over 4 to exceed 1, which means a squared must be strictly greater than 2. Now we apply these results to the three parts of the problem. Part A equals root 2, so a squared equals 2. This is exactly case 1. The equation holds for all x in the closed interval from 1/2 to 1. Part B, a equals 1, so a squared equals 1. Case 1 requires a squared to equal exactly 2. Case 2 requires a squared to be strictly greater than 2. Since a squared equals 1 satisfies neither condition, there is no solution. Part C, a equals 2, so a squared equals 4, which is greater than 2. Case 2 applies. Plugging in, x equals 4 plus 2 over 4, which equals 6 over 4, which simplifies to 3 over 2. That is the unique solution.